Hey there. I just wanted to talk about 7.3 in case you are not here because of the holidays, and in case we didn't get to finish it in class. So, long story short, 7.3 is basically 7.2, but 7.2 talks about the sampling distribution for sample proportions, and now we're just going to talk about sample means. Pretty much it. So, in this lesson, for example, like here they tell us we get samples of 50 pennies. 50 samples of pennies. Now we have samples where the sample size is 5 or the sample size is 20. So like this would be a sample of 5 pennies. Those 5 pennies have an average year of 1994, right? Or this sample of 5 pennies has an average year of 2012. Okay, so you get all samples of size 5 and you find their average, their X bar, and you plot them on a number line, and we have this shape, okay? You have samples of size 20. So in one sample of 20 pennies, you have this average of 1996. In 2 samples of size 20, you have the average year was 2005. So you get all samples of size 20, you find their sample averages, their X bars, okay? And you get this shape. So that's the idea that we're working with, is that we're gonna basically just get our samples, find their sample averages, right? Find their X bars, and all those X bars we're gonna plot on a number line, okay? That would be our sampling distribution. So like before, where the mean of p hat, like the mean of the sample proportions was just whatever the population proportion was, okay? So similar to that, when we do the mean of X bar, it's going to be whatever the population mean was. Okay, now standard deviation, before we just followed the formula, so we're just going to follow this formula. And best thing about it, these are all on your reference sheets. Okay, now same thing as in p hat, we are still going to have to check that 10% condition. We still have to check that our sample size is less than 10% of the population. Now, the reason why, okay, if we sample with replacement, okay, that means things are independent. That means our standard deviation is going to be exactly this formula. Now, when we sample without replacement, that means our standard deviation is actually going to be different, and it's going to be smaller than what the formula gives us, and that's way too unnecessarily complicated for us to do. So what we're going to do is just double check that the 10% condition works, and if the 10% condition is valid, even if we sampled without replacement, that formula that we have above is nearly correct. So we're just going to use this formula. Okay, so long story short, you do the 10% condition like we did before. So the number of movies viewed in the last year by students at a large high school has a mean of 19.3 movies with a standard deviation of 15.8. So this is for the whole school. So that's the population mean, and that's the population standard deviation. Suppose we take a simple random sample of 100 students, so our sample size, from this school and calculate the mean number of movies viewed by the members of the sample. Identify the mean of the sampling distribution of X. Okay, so the mean of our sampling distribution of X is whatever it is in the population, which is 19.3. Done. All right, part B, calculate and interpret the standard deviation of the sampling distribution for X bar, verify the 10% condition. All right, so 10% condition is the little assume sentence. So assume our sample size is less than 10% of our population, so of all students. At that school, I guess. All right, so now let's find the standard deviation for X bar. All right, it's the old standard deviation over the square root of our sample size. So our old standard deviation, 15.8, over the square root of 100. Square root of 100 is 10, so 15.8 divided by 10, 1.58. So if we were to interpret this, because it said find and interpret, all right, in a simple random sample of 100 students, the number of movies watched I guess we should say the sample, the average number of movies watched in our sample. So the average number of movies watched in our sample typically varies, right? So average distance typically varies from the true mean, right? The mean from the population, true mean number of movies by 1.58 movies. So the average number of movies watched from our sample typically varies from the true mean number of movies by 1.58. Okay. Honestly, the only thing that's different, in my opinion, is just this formula. The 10% condition is the exact same. Even the mean, all right? It's just you find the number from the population from your problem. And the standard deviation, the interpretation is the same. So the only difference is really the formula we just used. Now, if we wanted to know what shape it was, before we had to do large counts. We had to do n times p, see if that's at least 10, and n times 1 minus p, see if that's at least 10. We don't have p, though, when we're talking about x bars. So what we're going to end up doing is check, the first thing to do is check the shape. What is the shape of the parent distribution? If the parent population is normal, then no matter what size your sample size is, your sampling distribution will also be normal. So that's it. If they tell you it's normal, it's normal. Excuse me. Suppose that a population is normally distributed with a mean and standard deviation. Then the sampling distribution of x bar has the normal distribution with mean, again, same as what we just talked about, and standard deviation, same one we have above. So the heights of young women follow a normal distribution with means 64.5 inches and standard deviation of 2.5 inches. Find the probability a randomly selected young woman is taller than 66.5 inches. So we're just talking about one person. So this is a regular normal CDF type question. And how do we know it's normal? They told us. So normal CDF, we need 66 or taller. So 66.5 is going to be our low, or taller, so our high is infinity. Our mean is 64.5, and our standard deviation is 2.5. And you type that in, and we end up with 0.2119. Okay, so there's like a 21% chance that a woman is taller than 66.5 inches. Awesome. Now part B, find the probability the mean of a sample of 10 women exceeds 66.5. So it's not rare, but like 20% of women are taller than 66.5 inches. What's the chance that 10 of them are taller than 66.5? This should be, whenever you find your answer, it should be a smaller number. It's a lot harder to find 10 people to be taller than average instead of just one. So first we find the average. So the average of our sampling distribution is just the population average, so 64.5. The standard deviation of our sampling distribution is the old standard deviation over the square root of our sample size, so 0.79. And we also have to do the 10% condition. So assume 10 is less than 10% of all young women, which I think is valid. think there's more than 100 women. All right, now, how do you know it's normal for us to do normal CDF? It told us the parent population is normal. So the parent population is normal. So our sampling distribution of X bar is normal. Like, that's it. The parent population is normal, so is our sampling distribution. Okay. So we go ahead and we do normal CDF. And again, it exceeds 66.5, so that'll be our low. Our high is infinity. The mean of our sampling distribution is still 64.5, mean of our sampling distribution. And our standard deviation of our sampling distribution will be 0.79. We do that, that is way less likely, 0.0057. So while there's a 21% chance we find one person that's taller than 66.5 inches, there is a 0.5% chance that we find 10 people that average 66.5 inches or taller. So a lot harder to find 10 people than just one person. All right, so that kind of explains the following is, I'm going to zoom in here. Your population distribution, right? Let's say this was for the heights, okay? And our average is right here in the center, like it always is. To find like just somebody on one of the extremes, okay, you'll see like a decent amount of area, okay? To get 10 people, I don't know if you remember this, but I believe in 7.2, maybe 7.1, we said that larger samples produce less variability. They're going to be closer to that true average of 64.5. So larger samples, like our sample size 10 compared to 1, are going to be way closer to being on the average. So those extremes are going to be harder to find. Okay, like finding somebody, let's say somebody who's over, 7 feet tall. Finding one person taller than 7 feet tall is hard. Finding 10 people to be taller than 7 feet tall is going to be really, really difficult. Okay, so basically, remember averages are less variable than individual observations. Okay, one observation can be on the edges, right? Too tall, too short, whatever. An average number, okay? Usually a too tall person averages out with a short person, okay? When you have groups like samples, you will tend to have more area in the center towards that mean. All right, now, what if our population is not normal? What do we do? Okay, what if our population is uniform? If you have a small sample, like of size 2, you'll see that is not a uniform sampling distribution. All right, if our population was right skewed, again, if our sample size 2, still not normal. If our population is whatever that shape is, small sample size, still not normal. However, if you have a large enough sample size, so these are much bigger at 25, you'll start to notice that they're starting to look a little more normal. Okay, so that's basically this thing called the central limit theorem, which says that when n is large, all right, and for us, we're going to use at least 30. This website that I got this image from only went up to 25, but for our purposes, we're going to use 30. But when your sample is large enough, the sampling distribution is approximately normal. Okay, so that means no matter what shape the parent population is, you will have a normal sampling distribution as long as you have a big sample size. That's it. Okay. Keith is the manager of an auto care center. Based on service records from the past year, the time in, that should say minutes, because everything else is in minutes. The time in minutes that a technician requires to complete a standard oil change and inspection follows a right skewed distribution with a mean of 30 minutes and a standard deviation of 20 minutes. So we are already not normal right now. For a promotion, Keith randomly selects 40 current customers and offers them a free oil change and inspection if they redeem the offer during the next month. Keith budgets an average of 35 minutes per customer for a technician to complete the work. Will this be enough? Calculate the probability that the average time it takes to complete the work exceeds 35 minutes. Okay, so I want to know the probability that our sample average is going to be 35 or more. So already I'm thinking normal distribution. So to check if it's normal, I need to see the sample size because we already said it's not normal to begin with. My sample size is 40. So since my sample is 40, that's at least 30. Okay. By the central limit theorem, it's normal. So we're good. Okay. So what else do I need for normal CDF? All right, I need my mean. So the mean of X bar should be whatever the mean originally was. So that should be 30. All right, standard deviation. I need to use the formula. So standard deviation of X bar is the old standard deviation over the square root of my sample size. So that would be 20 over the square root of 40, which is 3.16. So that's what I'll write in here. With the standard deviation, we also have to check the 10% condition. So we're assuming 40 is less than 10% of all his customers. Okay. All right. And last thing we need the high and the low. And it's talking about exceeding 35. So 35 will be the low, and I need to go higher. So if we do all of that, we get our nice, lovely number. The chance of us exceeding 35 minutes on average is 0.0568. Okay, not too bad. So again, you're assuming we're probably going to do normal CDF. How do we know it's normal, even though it told us it wasn't? Okay, we look at the sample size. Our sample's at least 30. So by the central limit theorem, we know it's normal. And then to fill in the rest, okay, we needed to find the mean, which is just whatever the mean is in the population, which was 30. We needed the standard deviation, so we get the old one divided by the square root of the sample size. And because of the standard deviation, we have to check for independence, so we check the 10% condition. Now part B, how much average time per customer should he budget if he wants to be 99% certain that he doesn't go over budget? All right, we have a probability now. We have a percent. So we're not going to use normal CDF. We got to work backwards. We're going to do inverse norm. All right, now just a reminder, when you do inverse norm, it only shades to the left. So you just got to double check if what they just told you makes sense, right? Is this 99% to the left of our mystery number? If we want to be 99% certain we don't go over budget, okay, so 99% certain that we're going to be under a certain time, yeah, this scenario makes sense. Okay, we're 99% of our times should be under this mystery time. Okay, so we are shading to the left, so we are good to go. So we put 0.99 for our area. Our mean is 30, and our standard deviation is still 3.16 from the sampling distribution. So we go and fill that in, and we get a lovely 37.4 minutes on average per customer. If he does 37.4 minutes, he is 99% sure that he will not go over budget. All right. Last thing is the last thing from 7.2 as well, we're now going to be subtracting two sample means, okay? So we're going to have to check not large counts for normality, but we're going to check either A, that it told us it was normal, or B, that our sample sizes for both are large enough. We're going to find the new means by exactly what we did before. We just subtract the old means. And we're going to find the standard deviation with this lovely formula. It is, just like in the previous chapter, square them, add them, square root them. Okay? But they already did it for us in this formula. Right? Like our old, this was the standard deviation from this section already. So you square them. So that makes sigma squared over n. Hey, look at that. Sigma squared over n. All right, so you square both of them. You add them, you square root them. But again, it does it already for you in this formula, so you don't have to do the math work yourself. Just make sure that you know where to find this in the reference sheet. All right. A fast food restaurant uses an automated filling machine to pour soft drinks. The machine has different settings for small, medium, and large drink cups. According to the manufacturer, when the large setting is chosen, an amount of liquid, L, dispensed by the machine follows a normal distribution with a mean of 27 ounces and standard deviation 0.8 ounce. When the medium setting is chosen, the amount of liquid, M, dispensed follows a normal distribution with a mean of 17 and a standard deviation of 0.5 ounce. To test the claim, the restaurant manager measures the amount of liquid in each of 20 cups filled using the large setting and 25 cups filled using the medium setting. Let X bar L minus X bar L M be the difference in sample mean amounts of liquid under the two settings. That's a lot. Part A, what is the shape of the sampling distribution of X bar L minus X bar M? Y. So let's go back. What do we know about the shape of L and the shape of M? I know L is normal, and I know M is normal. So no matter what my sample size is, if I know my two distributions are normal, my two parent distributions, I know my two, the difference, the sampling distribution will be normal. Okay, so part A, the two parent distributions are normal. So X bar L minus X bar M is also normally distributed. Okay. Part B, find the mean of the sampling distribution. Okay, so the mean of X bar L minus X bar M is just whatever the mean for the large cups was minus whatever the mean for the medium cups was. So the large cups had an average of 27 and the medium had an average of 17. Now, just a reminder, if they had made us do M first, okay, we would have gotten 17 minus 27. We would have gotten a negative average, and that's okay. All right, that's just saying on average, medium will be smaller than large. Okay, so just a reminder that when we do the subtraction, you could get a negative average, and that's okay. In this case, right now, large tends to be a bigger number, so we're getting a positive answer for the mean. All right, part C, calculate and interpret the standard deviation of the sampling distribution. Okay, so standard deviation. I'm just going to follow this formula. Okay, I'm going to do, I believe it was 0.8. All right, so that's for large is 0.8, and the sample size was 20. So 0.8 squared over 20 plus, now for medium, it was 0.5, and the sample size was 25. Okay, you type all that up, you fill it in, and you end up with 0.205. All right, they want us to interpret it. So I'm just going to write that down here. All right, so the difference when we do large minus medium in sample means sample mean amount of liquid. All right, typically varies, right? Average distance, we need that. All right, so it typically varies from the true mean difference, or the true difference in means. Right, which was 10 ounces. By about 0.205 ounces. I'm not going to get too caught up with the interpretation right now. Okay, but in chapters 8 through 11, we are going to need to draw some conclusions. So we're going to need to get used to this kind of language. All right, now, technically, for standard deviations, we should be doing 10% condition, right? To make sure that if we're sampling without replacement. So if you want to say something like assume 20 and 25 are less than 10% of, I think 20 was for large, of all large and medium cups, respectively. You totally could, but technically there was no replacing. Like it's the whole point of the 10% is because you're not sampling with replacement. But with a soda machine, you literally can't like replace the soda. So it's not like we're sampling without replacement. Or if you're taking a sample from a river or the ocean, right? Like you can't really like, I guess you could take a sample from a river and then pour the water back, but like that's not, like the river is not like it has a finite amount of water, like it's going to continuously run. So since it's from a quote unquote infinite amount of soda, you don't technically have to use a 10% rule. Now, if you're like, Ms. Moser, I have no idea what you're talking about. To play it safe, you are more than welcome to do the 10% rule every single time. They're not going to mark you off for that. I'm just saying technically, if you're taking a sample from something that is infinite, like a soda machine is, quote unquote infinite, then then you don't have to do the 10%. Excuse me. All right, let's finish this off. Estimate the probability that the difference in sample means is within 0.25 ounces of the true difference in mean. Okay. So you guys already showed that it was normal. So we'll do normal CDF. So low, high. All right, so our mean, you guys, the difference in means was 10, right? Difference in large minus medium. And the standard deviation of the difference in the sample distribution was 0.205. So now it's said to be within 0.25 of, how did it say? The true difference in mean. The true difference in means. All right, so what does this really mean? All right, our true difference was 10. So we're going to go 0.25 less to find what the low is. So that's 9.75. So that's going to be our low. And we're going to go 0.25 higher to see what our high is going to be. So 10.25. Okay, so when it says within however much, that just means start at your average and go that much down and go that much up to figure out your low and your high. So when we go and we do that, we end up with 0.7774. So there is a 77.74% chance that we will be within 0.25 ounces of the true difference in means. Okay. It's kind of the same deal as before. The main difference here is we've been talking about averages instead of proportions. Okay. We are still doing what it looks like, right? One average minus the other average. So that's all we did with just the population numbers to find the mean. Standard deviation, I'm just following the formula that the formula sheet gives me, just like we did before. To check normality, we still have to check normality, but instead of large counts, since we don't have P, we either check that the two parent distributions are normal, like in this one, or we check that, like we had over here, that our sample size is greater than 30. Right? Central limit theorem says that would give us normality. Okay. Technically, we still do the 10% condition. In this particular case, you don't have to, but if it makes you feel better, you could always do it just in case, like we did here. Like, I'm pretty sure in a quote-unquote infinite amount of soda, I'm pretty sure 20 is less than 10% of infinity, and 25 is less than 10% of infinity. Okay, and then we just put all that together. You said it was normal. We have the mean and the standard deviation from before. All right, and then we just use that last sentence to figure out the high and the low. And that's it. Okay, so you do have some problems assigned for this, so go and look in the chapter 7 folder. I have the classwork assignments and the numbers with the page attached. Just make sure that that is done by the first time I see you after break. So A day, that would be on Monday, and B day, that would be on Tuesday. So just make sure you have the 7.3 work done and completed by the time you come see me. Other than that, if just a reminder, so 7.3 is due when you see me. Your project proposal is due by that Friday, January 10th. You are welcome to turn it in early by December 27th, and you'll get some extra credit. Otherwise, you're welcome to come and talk to me when we come back from break, and you turn it in by the 10th. And also on either the 10th or the 13th, okay, the third time I see you after break, we'll take 2 classes to review, but the third time on the 10th for A days or the 13th for B days, you guys will have a chapter 5 through 7 test. As a heads up, I put any of the review that we're going to talk about when we come back from break, I put everything up online early. So if anybody wants a heads up, you are welcome to look at it. But otherwise, we will be going over that when we get back in January. All right, if you guys have any questions, I'll try to at least check my email like once a week. So if you have any questions, you're welcome to email me. But otherwise, I hope you guys have a wonderful break, and I will see you back in January. Bye.